when you read things like, ventilation will reduce the transmission of COVID or influenza by 70%, where do they get those numbers from? What they don't do is they don't expose hundreds of people to a deadly virus and then, based on what works and what doesn't work, figure out the statistics from that. No. What they do is they use computer models. And so essentially what this means is they take all of the combined information we know and understand about the complex process that is airborne disease transmission, and based upon our understandings, place them into a model and then see how different mitigation strategies affect the likelihood of a successful disease transmission. Now, in this video, I'm going to walk through the different kinds of models people have developed over the years to study airborne transmission. And in doing so, try to explain what these models do, what they don't do, and how you can use the information from these models to help mitigate airborne disease transmission.
Prior to the 1950s, it was largely thought that diseases weren't actually transferred through the air. Now, this all changed with the Wells-Riley tuberculosis study. In their study, a system was set up at the VA hospital in Baltimore where the air from a TB ward was directed into a separate room that housed 150 guinea pigs. Now, what they found is that the guinea pigs were infected through the air. To conclusively prove this, they repeated the study, but this time they sterilized the air using UV ultraviolet germicidal radiation, also known as UVGI. This led to no guinea pigs being infected. Now, this work was revolutionary for a number of reasons. First, it demonstrated conclusively that tuberculosis is airborne. And second, it showed that UV can be used to clean the air and limit airborne transmission. Now, from this work also came the Wells-Riley model, a simple model of airborne transmission. The Wells-Riley model estimates the risk of airborne disease transmission, so PI, as a function of a couple different parameters. First is the concentration of infectious dose in the air. So this is the quanta value, which will be proportional to the amount of infectious virus that's suspended in the air. B is the breathing rate, so essentially how much air you're breathing at a certain cadence. And time, so essentially how long you're going to be sampling this air through breathing. And so with these simple inputs, the model estimates the probability of one or more infectious doses of being inhaled, so this PI value. Now, intrinsically, this all makes sense. The more infectious species that's in the air, or the more air that you breathe over time, is going to increase the risk of transmission. That said, there are a lot of factors that are just not considered in the model as it's currently written. So things like airborne viral decay or ventilation and filtration rates just simply aren't included. But that's one of the great things about the Wells-Riley model is that it can be easily adjusted to include these other parameters. However, other factors are not so easy to include. Location, for example. The Wells-Riley model assumes that the room is well mixed. The basic version of the model assumes that the concentration of the infectious dose doesn't change with location. This, of course, is not accurate.
So originally developed over 50 years ago, to this day, the Wells-Riley model remains the standard model people use to estimate airborne disease transmission. Now, it's really because of its simplicity, and it's because of this it can be readily adapted to include other parameters to, things like airborne viral decay. These kind of things can be readily integrated into the model to increase its overall utility. That said, there's some fundamental issues regarding the Wells-Riley model. It's this oversimplicity that limits its accuracy or the ability to estimate airborne disease transmission in some important ways to consider.
When it comes to airborne disease transmission, distance is critical for a number of reasons. Over short distances, the infectious dose is the highest in both the number of infectious aerosol, but also the microbes themselves will be fully viable immediately upon exhalation. In short, if someone coughs in your face, the risk of transmission will be higher than if you are, say, across the room from the infected person breathing. That said, the risk across the room isn't zero. Over time, the exhaled aerosol will travel throughout the room and over time may even become evenly distributed throughout. However, during that time, the infectivity of the microbes in the aerosol will be reduced, and the larger aerosol may settle to the ground, and others may be removed through ventilation and filtration. Thus, to readily understand and predict the risk of transmission, one needs to, at the very least, consider the complex processes occurring in the exhalation plume. The dynamics in the exhalation plume will affect many things. For example, from the simple, like how the aerosol in the plume will spread throughout the room, to the more complex, like how human behaviors such as masking will affect on how far the aerosol plume will travel. Thus, in order to estimate these kind of processes, scientists need to use more complicated computer models.
So if distance is really important for estimating transmission risk, then the Wells-Riley model, which assumes uniform mixing, really isn't ideal. Now, you can make subtle modifications to the Wells-Riley model to, say, break it up into short distance transmission and long distance transmission. That's one solution. Another solution is to use something called computational fluid dynamic modeling. And with this, what you do is you model essentially where the exhaled aerosol travels through the room and for how long, and based upon that, estimate the likelihood of disease transmission.
Computational fluid dynamic models were originally developed to, as the name suggests, understand problems that involve the interaction of fluids. Now, in 1935, Walter Findenson published the first aerosol CFD model to predict where aerosols deposit in the lungs. It wasn't until the early 2000s that CFD models began to be used by aerosol scientists to explore airborne disease transmission. Since then, CFD models have become widely used and an incredibly powerful tool to estimate how an aerosol will travel through a room. That said, unlike the Wells-Riley model, they are very computationally heavy, meaning that they take a long time to calculate, often using supercomputers to make their calculations. Additionally, they are highly specific. Thus, if you want to estimate the risk in a specific room, you'd have to calculate the risk each time a condition is changed. Despite this issue, CFD models are extremely useful for us to understand how an exhaled aerosol will physically travel through space. It allows us to see how physical interventions, such as an open window or a mask, even a poorly fitted mask, can reduce the amount of exhaled aerosol in a given space. In short, CFD models track the trajectory of countless particles over a given time period. Factors such as initial velocity and direction, wind speed, temperature gradients, physical barriers, and more are all included within these models. Based upon their outputs, one can easily visualize where the exhaled aerosol is carried and where it isn't. In short, CFD models are excellent at estimating transmission risk in controlled environments such as an airplane or a train. Moreover, they're extraordinarily powerful tools we can use to understand our indoor space. And I would encourage you to look at outputs of a lot of them, as they will give you a good idea of how aerosols flow through a given space across a given range of conditions.
Okay, so CFD models are excellent for understanding short distance transmission. And the reason for this is that they're very good at modeling the exhalation plume. So the exhalation plume is the cloud of infectious aerosol that leaves your lungs with every single breath. And so CFD models can be used to understand essentially how that plume flows throughout the room and how various parameters in the room affect where these plumes go.
All right, so the exhalation plume is the packet of air that contains all of the exhaled air and aerosol within a person's breath. The larger exhaled droplets, due to their size and speed, will rapidly exit the plume and simply fall to the ground. Now, the smaller aerosol will, for the most part, remain within the plume as it evolves and moves throughout the room. The initial volume of the plume is equal to that of a single breath, so typically around 400 to 500 milliliters. The temperature of the plume at the point of generation is about 34 degrees Celsius. The temperature of the plume is critical as its temperature dictates how it moves. The reason for this is because cold air is denser than warm air. This is why warm air rises. Warm air is literally lighter than cold air. And much like how any light object will bounce off a dense object, the temperature difference between the exhalation plume and the room air will dictate how far forward the plume travels. What this means is that as the room gets warmer, in this case from 17 degrees to 20 degrees C, the plume will travel further as it is carried upwards. The distance the plume travels forward before rising will highly depend on the temperature of the room. The plume will eventually reach the ceiling, and over time the temperature of the plume will lower, resulting in the aerosol being mixed more evenly throughout the room. This is one of the reasons why high ceilings is so important for limiting transmission. The high ceiling results in the virus of the plume physically being diluted more. On top of that, it provides time for the virus to lose infectivity before being eventually inhaled. Now, when the ceiling is short, the plume reaches the ceiling sooner and thus more readily travels across the room in a shorter period of time. And again, there's less time for the virus to decay and less volume for it to be diluted into before being inhaled across the room. Many factors will affect how an exhalation plume behaves. For example, a ceiling fan will break up these dynamics, resulting in the aerosol being equally distributed throughout the room faster. Likewise, ventilation will also affect these dynamics. A mask, even a poorly fitted surgical mask, will also affect these processes. That said, understanding these processes in a very general sense is useful. I would encourage you to look up as many images of CFD model outputs of exhalation as you can to try and get a better idea of how exhaled aerosol flows through a room. Plus, they're pretty neat to look at.
Okay, so just to summarize, when you're talking about modeling airborne disease transmission, you kind of have the spectrum. So on the one side, you have highly specific, highly computationally heavy CFD style models. And then on the other side, you have the fairly simple, straightforward, largely oversimplifying Wells-Riley type models, but they are still useful because they can, consider things like ventilation, filtration, this kind of thing. Since 2020, a lot of groups have come out and started releasing their own version of these models where they try to thread the needle, so to speak. And so in doing so, you get a little bit of best of both worlds. So CERN has one of these kind of models. I'll put a link down in the description for this model. It's a really nice, simple user interface. You should check it out. Okay, so with that, I hope you found that useful. I hope you found that interesting. If you like this, please like. If you want to see more of these, please subscribe. If you have any questions, put them in the comment section or ask me on Blue Sky and Twitter. And so yeah, with that, Mix has all the references that were used to make the video. Thanks.